Okay, so yeah, welcome to the very last lecture of this course. I hope you've enjoyed the journey so far. So there's this last bit of network security that we need to wrap up. Let me see, I might just do a very high level overview, right? So we started off by looking at what is security, and we looked at these four aspects of security, essentially confidentiality, where only the intended recipient should be able to understand the message. And this is achieved by encrypting the message so that only the intended receiver can decrypt the message, right? And then the next two things is what we are actually going to focus on today. First one being authentication, where the two endpoints might first want to confirm the identity of the other endpoint before they even start sending messages. So this is sort of the first step you would want to do, because you want to be sure that the entity you're communicating with is indeed the correct entity that you intended to communicate, right? Because if you start communicating with the wrong entity, then you may potentially be in trouble. Next is the issue of integrity of the messages themselves. So since the most applications on the internet are exchanging messages, and particularly some of these messages may be sent asynchronously, right? The other endpoint may not necessarily be active at that time. The other endpoint needs to be sure that this message actually came from the claimed sender. And the other endpoint may also want to be sure that the message wasn't actually altered along the way, right? So that aspect is referred to as integrity, and that's something we'll look at. This last point, unfortunately, we won't have time to cover in this course. So this has to do with ensuring that the services are available to the genuine users. And this ties in with this whole notion of denial of service attacks, right? So if attackers are able to send requests to whatever services you're providing, be it a web server, be it whatever server it might be, and they overwhelm your server such that the genuine users cannot actually connect, then we have a problem, because then the service is no longer available and accessible to the intended users. Then we started looking at, of course, this sort of abstraction of Alice, Bob, and Trudy. We looked at encryption, specifically starting off with what is referred to as symmetric encryption, where the two endpoints are using the same key. So the sender takes the plain text, applies this key, generates a ciphertext, and the receiver does the exact opposite, right? Takes the ciphertext, applies the same key, but to a decryption algorithm, and generates the plain text. Now, mind you, the algorithms here are known, right? So that's the thing with encryption, that everyone knows the algorithms. Like there are some examples later in this slide, right? Like DES, AES. So the algorithm is certainly known. However, what prevents any random person from doing this transformation is that they do not have this key. So the key is the secret here, right? So that is what is sort of hiding the information. Okay. Then we looked at some naive examples, and then looked at two ways to do symmetric key encryption. So one is where you're encrypting one bit at a time. So this is typically popular with streaming data, where you don't necessarily know the size of the data. And then the other approach is, of course, doing it as a block. So you break up the data into K blocks and encode one block at a time. So in terms of actual examples, of course, with streaming cipher, there's a bunch out there: RC4, Sober, Seal, and so on and so forth. And when it comes to block ciphers, we have this DES and AES algorithms, right? And then we looked at this issue of in block ciphers, if you have the same plain text, it maps to the same ciphertext. So how can we randomize this? So we looked at this whole notion of chaining blocks, whereby the ciphertext of the previous block is combined with the next message, the next block of the message. So this basically acts as the randomization vector for this message, right? And so we are doing this chaining with the exception that for the first block, you would need a distinct random input because there's no preceding block at that point, which has already been encrypted. So this is referred to as the initialization vector. Okay. Next, we looked at a radically different approach called public key crypto. And here the notion is you create a pair of keys in a certain manner. The public key is known to everyone. However, there is no way for someone to take your public key and then map it to the corresponding private key, right? So the way this is used is when Alice here wants to send data to Bob, she encrypts the message using Bob's public key, which is known to everyone. So anyone who wants to send encrypted data to Bob should be using Bob's public key, okay? And when Bob receives that encrypted message, Bob would apply his private key, and this would generate back the original message, right? So this was it's a very clever idea, and it works perfectly fine, right? So we looked a bit at some examples, a little bit into why that works. It's all based on modulo arithmetic. And then one key point which will be relevant in today's discussion is the order in which the keys are applied don't matter. So when you're sending encrypted communications to a recipient, Bob, you would use this approach. You would encrypt the message using Bob's public key, and then Bob would take this ciphertext and apply his private key, and that gets back the original message. However, if you change the order in which the keys are applied, so if you apply the private key first and then apply the public key, you still get back the original message. And this will be relevant today when we talk about signatures a little later. So let's now get right into that. We'll start off by looking at this notion of authentication, right? So remember here, when we talk of authentication, we have two entities that are communicating over the internet, and they're trying to authenticate each other. Now, who might these two entities will be? Well, they might really be two individuals, Alice and Bob, right? Because when Alice is sending messages to Bob, Alice may want to be sure this is indeed Bob and not someone claiming to be Bob. It could very well be two routers exchanging messages. It could be a browser confirming that the server is indeed the genuine server. And so on and so forth, right? So really this applies to any networking entities that are communicating. In our abstraction, we refer to this as Alice and Bob, and we refer to the attacker as Trudy, right? Now, in all these examples, I'm only going to show you one-way authentication, right? So here, the goal is that Bob wants Alice to prove her identity, right? So Bob is the one that's verifying the identity. Of course, in a real communication scenario, you might need to do authentication both ways, right? Bob wants to confirm that this is indeed Alice, and then Alice may also want to confirm that this is indeed Bob, right? But the same concepts apply, right? So whatever I'm showing you in this direction can also be used in the opposite direction, right? So just remember that. Okay, so let's start building towards a workable solution. So here we'll walk through a series of protocols, and as you'll see, the first few protocols I'll show you will have obvious holes, and then we'll try to plug those holes as we move forward. So in this first protocol, we are saying that Alice sends a message saying, I'm Alice, and then the assumption is Bob believes that this is indeed coming from Alice. Now, obviously, it is probably easy for you to figure out the problems with this, because what is stopping Trudy from sending a message claiming that she's Alice, right? Because remember, the attacker has a complete access to the communication channel, and the attacker can create these false messages. And there is this very classic cartoon by Peter Steiner. I think this was in the New York Times several years ago. So this is a often referenced cartoon when people talk about this issue of authentication and privacy on the internet, right? So it's basically saying on the internet, nobody knows you're a dog, right? So you could be anyone essentially. So of course, this is not going to work. Well, you might say, okay, let's improve this protocol and let's include a identifier, actual network identifier, right? Rather than just a message, let's ask Alice to also embed her source IP address. And let's assume Bob actually knows Alice's source IP address, right? So if he sees a message coming with that particular IP address as the source IP address, and then the message also contains this text saying, I'm Alice, Bob can be assured that this is indeed Alice. Well, no, this is again not going to work, because what's going to stop Trudy from creating an exactly similar message? Assuming Trudy can figure out Alice's IP address, which she can by snooping on Alice's traffic, she can create a message and the source IP could match Alice's IP, and she could again embed I'm Alice in here, right? So we again have a problem there. Well, you might say, okay, let's try to be a bit clever. And not only does Alice include her IP address and a message saying I'm Alice, we may assume that there's a shared, a secret password that Alice is using, and that's also known to Bob, right? So when Bob receives this, and assuming that only Alice and Bob know this password, then Bob can be assured, right, that this is Alice, because the source IP matches Alice's source IP. The message contains I'm Alice, and on top of that, it contains Alice's password, right? So what's wrong here? Well, Trudy certainly doesn't necessarily know this password. So how could she launch an attack? Well, again, remember here, the assumption is Trudy can sniff any messages being communicated, right? So what Trudy could potentially do is, sure, the first time she won't know Alice's password, but she can certainly eavesdrop on this channel, essentially, keep hearing the messages, capture this message, and then play it at a later time, right? So after that initial capture, she can essentially replay this exact message and send it to Bob, and Bob will now think, yes, this is actually Alice, whereas this is in practice Trudy. So this is classically referred to as a replay attack, where an attacker has simply captured a message and just replaying it at a later point in time, right? Or a playback attack. Yeah, it's the same thing basically. Well, you might say, okay, let's make the secret password encrypted, right? So let's add an extra layer of encryption. And assuming again here, you could use either public key, private key encryption, doesn't matter. We say the password itself is encrypted, so Alice cannot actually understand that password. Well, no, this is again problematic because it still exposes you to the replay attack, right? Alice doesn't necessarily need to understand this, right? All Alice is doing here, sorry, not Alice, Trudy, I'm sorry. Trudy doesn't necessarily need to know the password. All she's doing here is capturing that message and just replaying it, right? As long as she knows it contains something that Alice is using for authentication, she can simply capture it without necessarily having to know what's inside, and then just repeat that message at a later time, right? And then yes, Bob would still be fooled, and we are not stopping this playback attack at all. So can we actually solve this problem in real life, right? So let's look at something that's actually workable. And here we are introducing a important notion in security referred to as a nonce. This is nothing but just a random number that is only used once in a lifetime. So this random number is only active, you may say, for a very short duration of time, right? So how does this work? So here the assumption is that there is a shared key between the two endpoints, right? Now I know this is a fairly strong assumption, given that these, remember, authentication happens, authentication is the first thing that happens when two nodes communicate, right? Two entities communicate. Once they authenticate with each other, then they start exchanging data, right? So here we are assuming that there is already existing a shared secret key between these two endpoints. So this, if you think about it, this could only be possible if there's been some prior contact or communication, or something has happened whereby the two entities have actually established this shared key secret beforehand. Right now, you could certainly do that using public key crypto, as was discussed in the slides last week in the lecture last week. So you can certainly look that up. So that could be one way where the two endpoints could have established this shared secret, and then they go through with the authentication. Okay, so based on that assumption that there is a shared secret, this is how the protocol works. So Alice sends a message saying, I'm Alice. Bob generates a random number, which is this nonce, and Bob sends it back to Alice. Alice encrypts this message using this shared key that only she and Bob know. Bob receives this. Since Bob knows this shared key, Bob would do the decryption, and Bob would get back this same R, right? If it indeed came from Alice, right? So that's how it works. Now, the reason this works is, of course, this R is only active for a short duration of time. So maybe just enough time for this message to be sent to Alice and for her to send back this, right? So imagine you have Trudy here, right? Trudy is overhearing all of this, right? So Trudy, remember, Trudy doesn't have this key. This key is not known to Trudy. So Trudy may certainly capture this. Trudy may certainly capture this, right? And capturing this doesn't really help Trudy much, but what she can do is she can look at what Alice sent and she can try to replay this at a later time, right? So she can again first say, I'm Alice, okay? Bob will now send back some nonce to her, right? But remember, this nonce will not be the same as this nonce, right? So when Trudy is at a later time, right? Because this cannot happen at the same time. So the assumption is this is happening at a slightly later time, because for Alice to, for Trudy to have captured this, she needs to have seen this message, right? So when Trudy sends this message, Bob would send back a different nonce. And so if Trudy played this back, right, this would not match. When Bob did the decryption, he would see that this is not matching R prime, because this is a previous nonce that was captured. It's not the current nonce, right? So this playback attack is no longer possible, right? So that is that's how this works. Now there is a drawback, and in fact, one of you has pointed out this is vulnerable to man in the middle, and yes, it is. And in fact, I'll show you how this is vulnerable in just the next few slides. So that's a good point. The other issue is, of course, the reliance on a shared key existing between the two endpoints, which may not always be possible in practice, right? So given that, can we, and given that we know we have public key crypto, can we actually use public key crypto directly to do the authentication? Actually, let me go back to the man in the middle problem, Dharam. So in fact, man in the middle is not possible here. Sorry, I misspoke. Right. So the example I gave you actually is a man in the middle sort of scenario, right? In that Alice has sort of, because Alice, this Trudy, the intruder, doesn't have access to this key, so she cannot directly insert herself in the middle, right? So all Trudy can do is record these and replay them at a later time, right? The assumption being that this key is only known to Alice and Bob, right? So if you say Trudy has inserted herself here, the assumption then would be Trudy has established a shared key with Bob, and then Bob already knows that this shared key exists with Trudy, not with Alice, right? So there's no way to sort of do a man in the middle in this scenario. A man in the middle is possible in the next setting, the public key crypto setting that I'll explain to you. So let me first do that, and then I'll explain the man in the middle attack there. So this fifth version of this protocol is now making use of the nonce again, but now it's relying on public key crypto rather than symmetric key. So there is no assumption that there exists a shared key between the two endpoints here, right? So the way the protocol works again is Alice says, I'm Alice. Bob generates this nonce, sends it back to her. Now this time Alice will encrypt the nonce using her private key, right? So remember, this is different to the encryption we've seen before. It's this entity that is encrypting it using her private key. Okay. Bob then says, okay, send me your public key. Alice would reply back with her public key. Bob will then do this computation and generate back the original nonce. And at this point, he knows that this is indeed Alice, right? Because only Alice could have encrypted this message, since only Alice knows her private key, right? So if someone else had encrypted this, this would not match because this would be someone else's private key. Right? Okay, so now this works generally, except for the attack that Dharam actually mentioned there, which is a very popular attack referred to as a, we'll call it a person in the middle, right? Why make it specific to a gender? So let's call it a person in the middle attack. So the way the attack works is as follows, right? So Alice does the same thing and says, I'm Alice. Now Trudy has surreptitiously inserted herself in the middle. Remember, that's perfectly possible. So Trudy basically plays back that same message saying, I'm Alice. Bob sends her back a nonce, as was discussed. Now notice what Trudy is doing. Trudy is encrypting this message with her private key, not Alice's private key, of course, because she doesn't have Alice's private key, and then sending it to Bob. Bob is still thinking he's communicating with Alice, right? He's, remember, this is happening over the internet, so Bob cannot actually see that this is Trudy. So Bob says, okay, send me your public key. Again, remember, he's thinking this is Alice. Trudy sends back her public key, again, not Alice's public key. When Bob applies this to this, he will get back R, and he now thinks Trudy is actually Alice, okay, because all of this has worked, right? Everything has worked as per the protocol. Trudy can continue that same protocol with Alice. I mean, this is strictly not needed, but this is just to convince Alice that she's actually going through that authentication. So she can send this same nonce here, get Alice to follow the steps, essentially send the encrypted version of the nonce, get Alice to send her public key, and so on and so forth, right? So Trudy can continue with that, okay? Now, at this point, she has basically inserted herself into this channel, right? So she has fooled Alice into thinking she's Bob, and she has fooled Bob into thinking she's Alice, okay? Which means she, this person has now inserted himself into the communication. And what that now means is, assuming these two endpoints are going to use public key crypto for encrypting the subsequent messages, right? Remember, this is just the authentication phase. After that, they would be actually exchanging messages. And let's assume they're using public key crypto to do this. So let's say Bob is now sending a encrypted message to Alice. Remember how we use public key crypto for encryption? We send the message using the recipient's public key, right, which is known. So remember, Bob is still thinking this is Alice's public key. So Bob encrypts the message using what he thinks to be Alice's public key, which is actually Trudy's public key, right? So when Trudy receives this, Trudy can decrypt this and then send the message to Alice, right? So when she's sending the message to Alice, she can actually make use of Alice's public key. So Alice is also fooled into thinking, yes, this is, I'm getting an encrypted version of this message. And she thinks, okay, yeah, this is coming from Bob. And then she decrypts it and gets the original message, right? So in fact, Alice has received the original message. So at a later point in time, if they need to communicate again, both of these entities would assume that the communication happened correctly, right? Because the recipient did receive the message which was sent. The message wasn't altered. But the problem is Trudy has also seen the message, right? Trudy has got access to that message by inserting herself in the middle of this communication. So that's the problem, that this attacker has also seen the message, which is not what we want. So I will talk of a solution later, but does anyone have any thoughts on how this might be avoided? Don't look ahead into the slides. If something comes up in your mind, feel free to jot that in the comments. Checking the timing. Well, this is all happening in right one after the other, right? So I'm not sure timing is going to solve the problem, because timing is not the issue here, right? It's the fact that because this reply is coming instantly back, so this nonce is only being used for this short time from Bob's perspective. So there's no issue. It's not like there's a playback attack or something like that happening here, right? Any other thoughts on what might be the mistake? Like, what is the key problem here? Forget the solution for now. What is causing the problem? Obtaining the public key outside the communication channel. James, you are kind of heading towards the issue, but perhaps could someone be a little more explicit on that issue? You are in the right direction. Todd is saying once in a lifetime code. Well, this is a once in a lifetime thing, right? This R is only active for this short duration. So we are already using that. That's not the issue here. There's another issue which has allowed Trudy to insert herself. Let me give you okay, maybe sender has no way to verify that the message is going to the correct receiver. Jack, yes, like James, you're on the right track. The key problem is here, right? So when Alice sent this message back, right, this nonce back, the expectation is that this is encrypted using, sorry, I keep referring to Trudy as Alice. When Trudy sent this back here, right, the encrypted version of this nonce, the expectation from Bob's end is that this was actually sent by Alice, but it's actually sent by Trudy, right? And so when Bob is requesting for this public key, what he gets, he thinks this is Alice's public key, whereas what he's getting is actually Trudy's public key, right? So if there was a way for Bob to look at this and say, hey, this is not Trudy, this is not Alice's public key, this public key actually belongs to Trudy, then Bob would be able to pick this up, right? Because Bob has been deceived into thinking that this is Trudy's, this is Alice's public key instead of Trudy's public key. He's actually thinking that he's communicating with Alice, whereas he's really communicating with Trudy. So this is the issue. If Bob could somehow have picked this up and figured that this was not Alice's key, but Trudy's key, then he would not be fooled, right? So that is precisely the problem here, that there is, in this example, there is no way for Bob to verify that this key is actually belonging to Alice. He's believing that this is Alice's key, and as a result, this was encrypted by Alice, right? Whereas this is Trudy's key. If by looking at this key, he could say this is Trudy's key, he would not be fooled because he would know he's talking to Trudy. So how do we prevent this? I'll come back to that in a few minutes later, right? So let's put this on hold and we'll revisit that. So the next thing to look at is the issue of integrity. There's a question, can you verify whether something was encrypted with a private key using a public key? Well, yes, because if you apply this key on that, right, and if you get back what was originally sent, that's a verification that this, whoever sent us this had is this particular person, right? Because it's attributing to this person, right? So if someone has encrypted this and then they send you their public key, and that gets you back the original message, that is a confirmation for you that this could have only been signed by, in this case, it's Trudy, but Bob is believing this is actually Alice, right? So And in fact, that's something we'll discuss right now when it comes to message integrity, which is tied into what's referred to as endpoint authentication also, or authenticating the source of the message really. So confidentiality, of course, this has to do with keeping the message private and secret. Now, sometimes the notion of integrity might be confused with confidentiality, but remember, integrity is different. Here we are talking about tampering of the message. We are not focused on protecting the message, right? So we want to make sure that the message is not tampered with. So you can implement message integrity without necessarily having confidentiality. You could do both, certainly, but you could do each of these independently as well, right? So encryption doesn't guarantee integrity. I mean, you might say, okay, if the message is garbled, if you have manipulated the message so that an attacker cannot understand it, how could they manipulate it? Well, they could just blindly manipulate the message, right? If the attacker can sniff your packets and then change something without necessarily understanding what they're changing, it's still considered as being tampered with, right? And now the question is, can you as a receiver detect that this was tampered with, right? So encryption doesn't solve that problem. We need a different way to ensure that the receiver can actually detect that the message was altered with, if it was, right? So yeah, a bit more about this. If you look at the standard for public key crypto, it says something like that. It is primarily for providing confidentiality. It is not intended to provide integrity. So irrespective of whether you're using public key or symmetric key encryption, encryption itself doesn't give you integrity, right? So we need a different means to achieve integrity. It's a different property. So how do we achieve this? One way is to mimic what we do in the physical world, right? So in the physical world, I know a lot of us are not signing stuff anymore, but if you go back a few years when you made a credit card purchase, you had to actually sign. You were given a printed receipt and you had to sign it, right? We still do certainly sign in person contracts, maybe if you're buying or selling a house and stuff like that, right? So digital signatures refer to something similar, except that's being done virtually, right? So the purpose is exactly the same. We want to make sure that the person who's actually signing the document is the actual person. So in other words, nobody should be able to send you a signed document claiming it came from me, right? Because you are not me, right? I am me. So we want to make sure that when a receiver receives a signed document claiming that this signature belongs to Alice, then only Alice could have signed that document, right? No one else could have signed that document. Even the recipient couldn't sort of fake a document and claim that this was sent by another person, right? And forged their signature in effect. So the primitive that we use here should be verifiable, should be non-forgeable, right? So any recipient should be able to take your document and check that, yes, this signature belongs to Bob, and so no one else other than Bob could have signed it, right? So something like that. So now how do we achieve this? Well, we already have a cryptographic primitive, which is public key encryption, that will help us achieve this. Except the way we apply the keys here is a bit different from how we do it when we are encrypting messages, right? So remember here, the goal is again not to encrypt the message. That you could certainly do that, but that is orthogonal to this discussion. So in these examples, our goal is only to sign the message to ensure message integrity, right? So the message itself is being sent in plain text. Of course, in practice, if you wanted to encrypt this, you could certainly encrypt this, right? But that's outside the purview of this discussion itself. So how do we do digital signatures? We take the message, we use the same public key encryption algorithm that we've seen before, except now we apply the sender's private key. So whoever is sending this message has to sign it with their own private key. And so what gets sent is the original message and the signature. So this is referred to as the signature that's being generated, right? So when someone receives this, say Alice receives this message, which contains the actual message in plain text and the signature. Now Alice can take Bob's public key again, okay, because this is Bob's private. This is being sent by Bob. So Alice can go and ask for Bob's public key, get Bob's public key, apply it to this signature. Oops, the pluses are a bit messed up. I'll fix that up. This should be up, not down, right, like that. And this should be mine. I'll fix up all these suffixes. But essentially, when you apply the public key to this, you would get back the original message, right? So in this case, Alice can be sure that whoever has signed this must have used Bob's public key, because otherwise this wouldn't have worked, right? So Alice can verify that only Bob could have signed it. Alice can also verify that no one other than Bob could have signed it. And more importantly, Alice can verify that Bob actually signed this message and not some other message, right? So it's kind of doing two things. It's ensuring that the message itself was not altered, and it's also ensuring the source of this message as to who sent this message. And this is actually can be used as proof by law. So you could actually take this to a court of law and submit this as official proof, right? And the court would believe you, assuming you've used these correct cryptographic standards, right? So there's a question. So it's like sending M twice. No, you're not sending M twice. You're sending this, right? So you're sending message and then you're sending a signature. So this extra bit here is the actual signature you're sending, which is essentially you take the message, you pass it through the, you encrypt it using the sender's private key, right? So I don't think you can say you're sending the message twice. You're sending the message and you're sending the digital signature along with it, right? However, there is, so this certainly works, but there is one key problem here. And the problem is that public key encryption is computationally very expensive. And we've looked at this last time. Even in that simple example I showed you on the slide, you saw that when you're doing the exponents, the numbers can be very large, right? So while all this works, if the message itself is very large, then this operation becomes extremely complex, right? If imagine sending an extremely long message, then you have to do a lot of computation to generate this key. So there is a way to save on this computation, and the way to do that is by using hash functions, right? So rather than sign the entire message, what we do is we pass the message through a hash function, and then we sign the hash function. Okay, so rather than signing the entire message, we sign the hash output. So this hash output is of a fixed length, irrespective of the size of the message. Depending on the specific hash function you're using, it will always output a certain X bit value, right? This is always going to be fixed in size, right? Now, of course, we need to be careful about which hash functions we use here. And we use what are called cryptographically secure hash functions, which means these functions are designed in a way such that it's very difficult to go reverse, essentially, right? So they will always produce a fixed size, what's referred to as a message digest. It's of course many to one, right? Given that any size message always maps to something fixed length. It is certainly possible that two messages could potentially result in the same hash output, but the likelihood of being able, so given a certain message, the likelihood of you being able to generate another message M prime, which also generates the exact same hash, is virtually zero, right? So if you have chosen a good hash function, the likelihood of that happening is virtually zero. The other property, of course, is you can't go reverse. So knowing the hash, you cannot go back and generate the original message. Now, in fact, if you recall the internet checksum algorithm, it can be considered to be a hash function in that it's always producing a fixed output. The checksum is always of this size, but obviously it's not a cryptographically secure hash function, right? Because it's very easy to fool checksum, right? As we have seen, I'm not going to go through these examples again, but you may recall that if you sort of strategically change certain bits, it's very easy to result in the same checksum. And then this would mean if you actually used something like this checksum algorithm for hashing, it would be a very poor choice because it's not going to meet some of these properties, right? So what do we actually use? So till a few years back, the MD5 was a very popular hash function, but it has been shown to be vulnerable. So more recently, we are using the SHA, or what's referred to as the SHA family. And in fact, the first version of this is also vulnerable. So the current standards typically either use SHA-2 or SHA-3, which are currently considered the gold standard when it comes to hashing. Now, mind you don't need to know the detailed specifics of all of this. That is a bit more mathematically involved to cover in this introductory course. So conceptually, how does all of this work? So now when we are using this instantiation of digital signatures, the first thing we do is we notice we are not directly signing the message. We first pass the message through the hash function, generate this message digest, and then sign the message digest using the sender's private key. Here, Bob is the sender, right? So this encrypted message digest is essentially digital signature. So this becomes the signature. So what gets sent out is the message and the digital signature. Right? Now, again, I'm repeating that here, since we are not focused on encryption, the message, we assume it's being sent in plain text. In practice, if you wanted to also encrypt this, you could certainly do that, but that's not part of this discussion, right? The goal here is just to provide message integrity. So what Alice receives, Alice will receive two things, the message and this encrypted message digest. Alice would take Bob's public key, apply it to this message digest, right? Do the decryption, and this would generate back this message digest, the hash. Alice would also know the hash function because this is again well known to both endpoints. She would pass the message through that, get the hash, and then compare these two. If these match, then Alice can be assured that no one else has altered the message and this message actually came from Bob and no one else could have generated this message, right? So this is ensuring integrity of the message and also the source of the messages as to who is actually sending it. Right? Okay, so this is showing you how to do this using public key crypto. Now there is a parallel way to do this using symmetric key crypto. So here the assumption again is the two endpoints have agreed on a key, right? They have a shared secret which is only known to them. So this algorithm is called a MAC, a message authentication code. And the way this works is the sender, again, you have the original message. You pass it through this MAC algorithm, which takes the key as an input. And then this generates essentially what's referred to as the message authentication code or the MAC. So what gets sent out is the original message and the MAC, the two things as you see here. The recipient will know this key, right? So they would take this message, run it through the MAC using that key, which is again a secret, generate the MAC and check if this MAC matches the MAC that was sent, right? And if so, the recipient can again be sure that this message has not been altered and this message actually came from this claimed sender, because only this sender would have known this key, right? The assumption is this key only exists between this pair. No one else knows this key. So in practice, again, there are various algorithms that implement MACs. So you see some names here. Again, you don't need to know them. This is just out of pure interest, right? So this could be another way to do message integrity, except here we are using symmetric key. The previous example shows you how to do it using a public key. Okay, so now it's time to revisit the original problem, which if you think about it, this problem will also arise here, right? So again, just to recap, Trudy here has inserted herself between Alice and Bob, and Trudy was able to do that because Bob sort of got fooled here, thinking this is actually Alice's key, but this is actually Trudy's key, right? So, of course, that's one issue that was noted earlier. You could also, I could also give you a more kiddish example, a little sort of naughty example of why we might also encounter this problem in the context of digital signatures. So imagine here Trudy wants to play prank on Bob. So Trudy could create an email order saying, hey, pizza store, please deliver 4 pepperoni pizzas. And Trudy could, again, in this case, sign the order with her private key, right? And send this order to the pizza store. And then what Trudy could send to the pizza store is her public key, but claim that this is Bob's public key, right? So in effect, it's very similar to that man in the middle attack that you saw there. The issue again here is that when the pizza store uses what they think is Bob's public key, but which is of course Trudy's public key, and applies them to this signature, it will make sense. It will all match, right? So this algorithm, the digital signature, will work because what they think is Bob's public key is actually Trudy's public key, right? So Trudy would be actually able to fool the pizza store, and the pizza store would send 4 pizzas to Bob, even though he probably doesn't even like pepperoni pizza, right? So again, this is a sort of kiddish example, but it's again making the point that this same attack is also relevant here when we discuss digital signatures. So how do we address that problem? In other words, how does someone actually, when they get a key, how can they verify that this key actually belongs to that person, right? So if Bob is sending Alice his public key, how does Alice verify that this is indeed Bob's public key and not someone else's public key? So for that, there is this whole notion of public key infrastructure or certificate authorities. So the assumption here is there are certain well-known third parties who are called certificate authorities, and they can actually attest someone's public key, right? So the way this would work is if Bob wants to get his key attested from this certificate authority, Bob would provide them with certain identifying information. Bob would give them his public key. The certificate authority would first verify that this is indeed Bob, and then they would certify, essentially attach a certificate to Bob's public key. Now, how do they certify this? Well, they take Bob's public key, which is being certified. They pass it through the same digital signature algorithm. And this time they sign, the CA is actually signing that key essentially. So the certificate authority's private key, KCA minus, is used to generate this digital signature. And then that becomes the certificate for Bob's public key, right? So imagine this here has 2 things. It has Bob's public key and then this signature that was generated by the CA attached to it, right? So when someone else receives, let's say Alice gets Bob's public key, how can she verify that this is indeed Bob's public key? Well, Alice sees that this was signed by a particular certificate authority. So she can apply the certificate authority's public key, which would be known to everyone, okay? So she could apply that to this certificate. And since this was signed using KCA minus, when she applied KCA plus to it, it would be able to verify that this was indeed signed by this certificate authority, and then she can be assured that this is Bob's public key, because this certificate authority has done the check and they've put their trust and they've affixed this certificate onto that, right? So that is a way for Alice to be assured that this was Bob's public key. If you go back to the man in the middle problem, imagine these were certified keys, right? So when Bob here checked this key, that check would reveal to him that this was actually Trudy's key and not Alice's key. So it would immediately avoid this sort of attack. Right? And the same thing here, it would avoid this attack because the pizza store could check that this does not belong to Bob. This public key actually belongs to Trudy. Right? Now, of course, there is some reliance here on third parties. So we are certainly assuming there exists such third parties who would do this. We have to trust these third parties, because if certificate authorities are not trusted, then we again have a problem. And there have been some security issues around this whole problem of dodgy certificate authorities providing fake certificates, right? So what does a certificate actually contain? This is, I'm sure you have seen some of these certificates and you have blindly clicked OK, but the next time you experience this, please have a look just out of interest, right? So it will contain all sorts of information. It will contain information about the certificate authority. So VeriSign, for example, is a very well-known certificate authority. It will contain the date and so on and so forth, right? So you can certainly have a look. So there are actual standards for this. So there's this X.509 standard, which outlines what exactly the certificate should contain, right? So this is all sort of referred to as the public key infrastructure, because we are relying on these trusted third parties, and it's also often considered heavy-handed in that there's this whole investment that needs to be made, right? So there is this other alternate way to sort of ascertain keys, which is referred to as the web of trust, whereby rather than relying on third parties, common individuals, we can sign each other's keys, right? So I can sign your key if I know you and I trust you, and you can sign my key, right? Of course, the weight of our assertions is probably less than these trusted third parties, but if you accumulate enough of these signatures from other individuals, then potentially other people may be able to trust that, given that you have gathered evidence from sort of multiple people. But if you're interested, certainly have a look at this web of trust concept, right? So there's a question, are the CAs basically hard-coded known, or is there a CA discovery mechanism? So yeah, there are certain CAs, I mean, the certificate that you get would contain the information about the CA, right? So all of this, of course, is not done by humans, right? It's done by some program. So based on the information in your certificate, that particular program that's doing the verification would go and communicate with that particular certificate authority, right? And of course, there are well-known CAs like VeriSign. I'm forgetting some of the other popular ones. Probably Symantec and some of these other security companies also do this, right? So yes, this is certainly, it's not like you can set up your own CA, right, on the fly. There's certainly some heavy investment and heavy checking going on before an entity can start issuing certificates, right? So it's a fairly heavy-handed process. Okay, so how about I ask you a question now? So let me do this. In fact, there's a couple of questions. So could you kindly answer this? So it's asking you if Bob wants to send Alice a digital signature for the message M, how does Bob create the digital signature? Okay, let's have a look. So most of you are saying Bob applies a hash function to M and then encrypts the result with his private key. And yes, that is perfect, right? That is the correct answer. That's precisely what's shown on this slide here, right? So Bob takes the message, passes it through a hash function, generates the message digest, and then applies his private key to generate the digital signature. So well done. Let's now take the next one. So suppose a certificate authority creates Bob's certificate, which binds Bob's public key to Bob. The certificate is signed by which of the following things? Obviously, it's the last answer, right? Obviously, it's not. That's just a joke. Oh, sorry, I forgot to activate. Sorry, yeah. Okay, let's have a look. Yeah, well done. The C is private key, right? So this is again explained here, where Bob's public key is signed by the CS private key to generate the certificate, right? So yeah, well done. I think seems to be making sense. Okay, so I know we are about halfway, but what I might do is I might actually just complete this last bit. Then we'll take a short break and then I'll do the wrap up and talk about the exam, right? So that way we kind of complete all the content. So just bear with me about 5-10 minutes more. So now that we've looked at all these concepts, here we are actually bringing all of them together in the context of a real application, right? So here I'm presenting to you an application which is implementing all these concepts in the context of email. So it's going to show you different ways you could, depending on what properties of security are being provided, it's showing you the different functionalities that you could implement. So in this first instance, we are only implementing confidentiality, right? So Alice wants to send an email to Bob and she wants to make sure that only Bob can read this email. No one else who may sniff on this email and capture this email will be able to understand this email. So how does Alice do that? So here we are going to use symmetric key encryption to encrypt the email. However, to generate that symmetric key, we are going to use public key encryption, right? Now, why, you might say, why couldn't we directly encrypt the email using public key encryption? You could certainly do that, but remember, public key encryption is very costly. So encrypting a whole email, particularly if the email is large, contains attachments, using public key encryption is just too much computation, right? And we know that symmetric key is much more quicker. So what we do is we use public key to just generate the symmetric key and then use symmetric key for the actual encryption. So how does this all work? So you'll notice here Alice first generates some random number, random key pattern, which forms the symmetric key, right? So this is just some random key of whatever length the is specified that Alice would generate, right? She then takes the message, encrypts it using this same key, okay, now KS. So here we have the encrypted version of this email. Now, remember, this key needs to be communicated with Bob, and this key needs to be communicated using public key encryption. So here you notice since Bob is the recipient, Alice is encrypting this key using Bob's public key, right? So what we have here is now an encrypted version of this symmetric key, okay, which is encrypted using Bob's public key. So she's now sending two pieces of information. One is the encrypted email itself. The other is the encrypted key, the symmetric key that was used for this encrypting the message. So when Bob receives these two things, Bob sort of splits them up. Now, of course, Bob cannot decrypt this until he knows what the symmetric key is. So the first thing Bob would do is Bob would take that encrypted symmetric key, apply his private key to that, and this would allow him to figure out the symmetric key that's used, and then apply that to this and generate the original message. Now, mind you, the assumptions here are the specific algorithms are known, right? So Alice and Bob know they're using a specific implementation of public key, a specific implementation of symmetric key, right? So that all of that is known. Now you might wonder, okay, what if someone else here in the middle gets access to this? Well, if they get access to this, firstly, they cannot decrypt this because they don't have KS. So they're never going to be able to figure this out. And they're also never going to be able to extract this key because they receive this, and there is no way for someone on the internet to decrypt this because they would not know Bob's private key, right? The assumption is that a person's private key is only known to them, right? So Trudy here would not be able to extract out KS, and as a result, she would not be able to read this email, right? So hopefully you see how this implements confidentiality, right? This slide is just explaining to you what Bob is doing, which I already explained. So we can move forward. So that was to do with confidentiality. Now this here is showing you how you could implement message integrity and authentication. So notice here we are not encrypting the message, right? So in this example, we are assuming the message is being sent in plain text. So how does this work? Well, this is fairly straightforward as we have discussed. So Alice would pass the message through that hash function. She would then apply her own private key to this hashed digest and then generate the digital signature. Would take the message and then, so essentially send these two pieces out to the internet. Bob, when Bob receives this, Bob would take the digital signature, apply Alice's public key. The assumption here is Bob can verify that this is indeed Alice's public key. So what's not shown here is the certification process, right? So the assumption is this has been certified, this has been certified, right? So when Bob receives this, Bob can verify that this actually belongs to Alice, right? Then Bob applies this, gets the hash, passes the message through this same hash function, gets the hash, compares, and if they match, then Bob knows that this indeed came from Alice. No one else could have signed it, and that the message itself was not altered, right? Okay, so now how about if you want to do both? So if you want to have integrity, authentication, and confidentiality all together, so how do we do that? So here we are showing you what's happening from the sender's point of view. So essentially it's combining both of those two things that we just saw. So the first thing here you notice is the integrity of the message itself is being achieved. So that is done using, as we discussed, you pass the message through the hash function, apply the sender's private key, generate the digital signature. Then we have the message. Now in the earlier instance, we were just sending this in basically the message in plain text along with the signature. Since we want to implement confidentiality here, what we do is we encrypt both of these, right? So here you notice the message and the signature are encrypted using the symmetric key, which is generated here. like you saw in the previous example, right? So the sender generates some random key, which is used for the symmetric key encryption. You encrypt all of this, generate this, and then you also encrypt the symmetric key using the recipient's public key, right? And then what gets sent is that and that, right? So on the receiver side, what I've not shown you, but you could sort of do this in your own, essentially figure out what the receiver does. It's essentially a combination of what happens here and what happens here, right? So the first thing that would happen is this. Bob needs to get access to that symmetric key and then extract out the message and the signed message, and then do these checks here to verify the signature, right? So now, of course, this discussion was conceptual. All of this is actually practically implemented in various instantiations of secure email. So one popular one is PGP, which stands for Pretty Good Privacy. So this is a fairly commonly used standard for email encryption. If you've installed PGP, the first time you do it, it will create your public private key pair. Your private key would, of course, be kept in your private keychain on your machine. Your public key, you can post it on your website. You can put it in your signature, email, wherever. I mean, your public key is meant to be public, right? So you can basically put it out there, right? And this gives you options to do both of those things. Essentially, you can just sign the message, you can encrypt the message, or you can use both. And in terms of the specific algorithms, again, it's uses the state-of-the-art algorithms. Like I think nowadays SHA is used for the digest, whereas it's using some of these other symmetric key implementations and RSA for public key, right? So this is just showing you an example of the actual signature. So this is just a purely signed message, and this is actually a completely encrypted message. So as you can see here, you can't even decipher what this message is, right? Okay, so that pretty much concludes the content. So what we might do, I might just wait if there's a question. If not, maybe we'll just take a 5-minute break, and then I'll do a quick recap, and then I'll talk about the final exam, right? So I'll see you in a couple of minutes. While you're on the break, of course, I need to show you the meme. This is an interesting one. This is from XKCD. So yeah, you can have a read through this. One final meme, I guess. Yeah. And I'll see you in a couple of minutes. So let me just pause the recording till then. Okay, so we're back. We're done with the content. Any final logistics things? Well, your labs are now done. This week, you'll be having the tutes. And I mentioned this in the last lecture, but effectively your tute questions are from past exams. So it's kind of like a sample exam by itself. I have finalized this page. Most of it is visible to you. I will make the sample exam also visible, right? So you can have a look through this. It talks a little bit about all the information that you need for the final exam. I've set up a Zoom link if you want to ask me questions. If you have technical problems, you will have access to some other, I think there's a phone number and stuff like that on your Moodle page, which should open up, which will allow you to talk to the exams people if you're facing any technical issues. For questions on the exam itself, you can just log into the Zoom session and ask me questions. I'll be online. The exam will be on Monday 6th from 2 to 4 with 15 minutes reading time. So most of it, I'll talk a bit more about the exam a little later today. Another thing I wanted to point out was the My Experience surveys. Now, unfortunately, the response has been pretty poor. I can show that to you. You can see the response rate. Oops, what happened there? Okay, so let's take a look at where we are at. So only 13% of the class has actually filled in the survey. So I know everyone's busy, but maybe once you're done with your assignment, if I could kindly encourage you to provide feedback. As you notice here, only about 60 odd people have completed the feedback, and there's a lot many who haven't, right? So would really appreciate if you could take that time. Other than that, there's not much. I will post some additional consult times for the exam period if you need to ask me any questions. So just be on the lookout for some further notices about that. And I will make this sample exam visible to you. In fact, I've also extracted the exam paper from Inspera, so I can make that visible. I can make the actual exam visible. So I would certainly encourage you to have a look and do the exam in Moodle, in Inspera, sorry, at least once, right? Okay, so let me now do a quick recap, and then I'll talk briefly about the final exam. All right, recap. So we have pretty much completed what was intended. So we are perfectly on track, on schedule. We've kind of, if you recall, when we started this course, we said we'll take a top-down approach, right? So we started off by looking at the end systems, essentially focusing on the applications and transport layers. Then we spent, I think that's got us till the midterm exam. After that, we spent some time looking at the core of the internet, IP protocol routing. Then finally, last week, we started looking at the link layer, which was Ethernet. And then we spent a brief amount of time looking at wireless networks and the basics of security. Right. So I think this course has given you a good overview of the entire protocol stack. You've got a good feel for how the internet works, particularly some of the key principles that are guiding the design of the internet and computer networks in general. So concepts like layering, how do you deal with scale, how do you organize networks in hierarchies, and so on and so forth. And then various design approaches that are used in the internet to implement some of the key functions, right? So things like how do you design the application itself? How do you implement reliable transfer of data? How do we do routing? How do we manage congestion? How do we manage access to media, particularly when the medium is a shared medium, like say wireless, and so on and so forth. And you've also got some hands-on exposure to using some interesting networking tools. Now, these are actually real tools that are used in the industry. So tools, of course, some of the command line stuff like ping and traceroute, but then you've also looked at Wireshark, which can be quite useful when you're doing all sorts of diagnostics, right? In the real networks, it's very common to actually capture traffic and examine it using Wireshark, right? And you even briefly got a peek into a network simulator, NS2. This is a very widely used network simulator, both in research and in the industry, particularly when it allows you to sort of simulate large networks and do some tests before you can actually deploy things on a real network, right? Which is a lot more work. And you also were able to work on a reasonably real world assignment. The interface is probably, you don't have some nice GUI, but at the fundamental level, it's hopefully still interesting enough that you were able to design this chatting application, right? It's something that we use all the time. I mean, I'm sure you're all using various chatting applications like, I don't know, Telegram, WhatsApp, WeChat, whatever, right? So hopefully this gave you a little bit of insight into what actually is happening, right? Under the hood, as they say. So some of the key topics we looked at was firstly, how do we sort of organize, given that the internet is so complex, how do we even organize all of this and study it? So we looked at layering, hierarchies, this whole notion of encapsulation, how each layer adds its own headers, and how the packet moves up and down the protocol stack. Then we spent some time looking at the application layer, where we talked about how do you design application layer protocols. And in fact, that's something you've done in your assignment as well. We briefly looked at P2P, socket programming, which you got a lot of exposure, particularly with your assignment. And then spent a lot of time on the transport layer, actually, where we looked at error detection, how do you implement reliable transfer of data over a fundamentally unreliable channel, and then the issues of flow control and congestion. And then, of course, the actual instantiations in terms of TCP and UDP. At the network layer, we looked at IP addressing. How do we deal with scale? How are the addresses actually assigned? The fact that IP addresses are not random, they actually have some hierarchy. Then we briefly looked at fragmentation, which essentially has to do with the link layer, the fact that the link layer technologies are heterogeneous, right? And then we focused on the control part. Essentially, at the network layer, you have essentially the control plane and the data plane, right? So the routing algorithms form part of the control plane, and we looked at two ways to implement routing. One which relies on global state called link state, and the other one which is distributed. So that's distance vector. And then finally, we got down to the link layer, the lowest layer that we study in this course, where we looked at MAC addresses, ARP, the issue of media access control, and in general, how your packets are actually moving from across multiple links, right? And the sort of interactions between the network layer and the link layer in order to do that. And then in the final, after we concluded that, we had a little bit of time left where we took a sneak peek at wireless networks, and then we spent a little bit of time understanding some of the basics of security, right? So what follows? So in fact, I should make an edit to this slide. So we've actually updated the offering a little bit. So next year, we will be offering a course called Advanced Computer Networks. This routing and switching won't be offered. So in its place, we'll have a follow-on course called Advanced Computer Networks, which is sort of following on from this course. And you'll learn some of the advanced stuff that we couldn't cover here. So if you found this interesting, I would strongly encourage you to have a look at that, because that will give you a more solid and deeper understanding of some of the networking principles. In fact, might as well. Oops. Yeah, I could just do this change live here. Yeah, that's the course. Perfect. Okay. Beyond that, if you're interested more in how networks are actually provisioned and planned, how do you sort of look at the managing the capacity of networks? So you could look at 9334. It's a little more analytical and mathematically inclined, but that can also be a very interesting course. If the aspects of mobile and wireless networks interest you, then we have a course on mobile and mobile data networks. We've also got a course which focuses on network security. There's a special, more hands-on course which looks at IoT, the Internet of Things. So this is a design studio where you get to work on a large project with some real hardware. And then there's a range of security courses. So you start off with the security engineering course, but then there's a number of other security courses also offered, right? And then, of course, you also have the option to work on undergrad or even master's projects on these topics, right? Yeah, so I think that's all I have to say about the recap. I might now move on to the final exam, which is probably going to be of interest to a lot of you. So just to remind you, your final exam is worth 40 marks. So the date is already announced. I will post the link to the actual exam closer to the date, but you can also find it on the Moodle page, just like you did for the midterm, right? So yeah, it'll run for 2 hours, and then I think you'll have 15 extra minutes reading time. The exam is actually all organized by the exam unit. So they manage this whole exam for us. So if there are any technical issues, certainly reach out to them. If you go to the Moodle page, you'll find there's some information there on who to reach out to if you have technical issues. If you have questions on the exam, then just join the Zoom meeting and you can ask me questions there like we did in the midterm. So the exam is worth 40 marks. It counts to 40 marks towards your final score. This is what I cut and pasted from the course web page. And you must, there is one hurdle. There was no hurdle for the midterm, but there is one hurdle for the final. You must score at least 40%. So that's basically 16 marks on the exam, right? It's of course open book, open notes. You can use calculators. Now, the amount of math is certainly much less on this exam compared to the midterm. You might still need a calculator for 1 or 2 questions, but most of it doesn't include any complex math at all. The exam is, of course, on the Inspera platform, the same platform we used for the midterm. And then, of course, all of these and other details will be on the final exam. So there's a question about scaling. I cannot comment on that. Scaling, I don't even know if I will need to scale. It really depends on the relative performance of this, of the entire cohort, right? So I cannot at this stage tell you whether or not I will scale, and if I scale, by how much. All of that is unknown, right? It entirely depends on how everyone performs on the final exam. So of course, a few things, you must submit your own work. You must not get any assistance from anyone. You better check all the policies around academic integrity. There's the fit to sit policy. So if you sit for the exam, you're assumed to be fit. And there are certain rules on how you could apply for special considerations. If you have registered for ELS, you will receive information about your specific arrangements a little later. So look out for some email on that later. So what is and what isn't on the exam, right? So this is talking about the content itself. What do you need to study? So one thing I can assure you, there won't be any questions on the content that's from the introductory slide set. So this is essentially packet switching, circuit switching, and some of there's computations. There might be some of that in the context of TCP or something else, but not in the setting that we looked at when we talked about the packet switching, circuit switching, and all that initial discussions, right? In fact, there won't even be any questions directly on any of the applications. So I won't be asking you any questions on HTTP, DNS, email directly. However, these applications may be referenced in the context of this whole discussion on the synthesis of protocols. And in fact, if you look at the sample exam I've given you, I think the last question is sort of based around this. So have a look at that last question just to get a feel for, if at all any of these applications are referenced, how they might appear in the exam, right? Because it's hard to completely disconnect and not talk about applications, given that we're talking of networks, right? But there won't be any direct specific questions on that. There won't be any questions on P2P, BitTorrent, or DHT. All of that is excluded. So what is on the exam? Well, The transport layer onwards, pretty much everything that we've covered in the lectures will be on the exam, right? So this includes the discussion on sockets, TCP, UDP, all this basic RDT, go back and selective repeat, congestion control, all of that is on the exam. Of course, I can't ask you very complex things when it comes to checksum and stuff like that, because that just becomes intractable to do, right? But I could ask you a general question on checksums, if at all. Then, of course, the network layer, which was covered after the midterm anyway. So everything that we discussed in the lectures is on the exam, with the exception of things that were explicitly marked, right? So you can expect some questions on IP addressing, NAT, IPv6, tunneling, and so on and so forth. Nothing on stuff that we didn't cover. Obviously, I didn't cover some of this discussion on what's inside or out SDN and so on and so forth. When it comes to the control plane, there were really only three things: link state routing, distance vector routing, and ICMP. We didn't actually cover specific protocols like BGP, OSPF, RIP, or this whole discussion on hierarchical routing, so that won't be on the exam. In the link layer, again, we covered a fair bit, like just some general discussion on the link layer, error detection, correction, if you recall, parity, CRC. Again, with CRC, if at all, I'll ask you a simple question. So I think the sample exam has a question on CRC, so you can have a look at that. But I'm not going to ask you like to compute a 32-bit CRC or something like that. That's not mathematically tractable. Questions on multiple access, switches, MAC addresses, ARP, all of that is fair game. And of course, the stuff we didn't cover, like virtual LANs, MPLS, data-centric networking, all of that won't be on the exam. And you might certainly get a question on this whole synthesis. So again, I refer you to that last question on the exam, which goes over some of this on the sample exam, I mean. Wireless networks, well, we didn't cover a lot, but you may get a question on some of the basics there. And security, again, whatever was covered today and in the last lecture, really, right? That's all that will be on the exam. So of course, there's no questions on programming. We won't be asking you to use any of the tools like in the labs. So it's not like we'll ask you a question, run this trace route, and based on your output answer. So no, nothing of that, right? You won't be asked to use any of the lab tools. In terms of the type of questions, so again, very similar to the midterm, we could have a range of different type of questions. There'll be a small number of multiple choice, not heaps, little few of them. A few where you are required to provide some justification. So a couple of sentences usually is enough. And of course, sometimes the questions may be sort of multiple questions, may be sort of part of an umbrella question, right? So multiple parts to that same question. So wherever asked, make sure you're providing explanations. The question will explicitly tell you where explanations are needed and where they're not. I mean, in some places, there is no space even to write the explanations, like when you're given a multiple choice question, obviously you don't provide explanations, right? And yeah, it's not an exam where you can find answers somewhere, right? So it's all about applying what you've learned in the context of that particular question. So again, I think the midterm exam is a fair representation, or in fact, some of the questions that are on the TUTs, in the homework questions, and some of those discussion questions. So it's all about trying to test your analytical skills. So it's very unlikely you would have seen the exact questions before. You might have seen flavors of those before, but not the exact same question, right? So it's not really a memory test. It's more about you being able to apply the concepts that you have learned. So let me take a couple of questions that came up Will it be harder than the midterm? That's a bit difficult for me to say. My feeling is it is easier than the midterm, but again, my feeling sometimes doesn't pan out to how the class feels. But my feeling is it is easier. But again, take it with a grain of salt, right? Maybe think of it to be harder. So then when you do it and you find it easy, you'll be very happy, right? Maybe I could say it that way. Can we have the breakdown? No, unfortunately, I can't give you that. But as it says here, there are some multiple choices, but there are not a lot of them. That's all I can say, right? Will it be similar in length? Well, it runs for a little longer, right? Your midterm was for what, 70 minutes, I think. This is a little longer. So the exam will be a little longer, of course, than the midterm, but I think time should generally be okay. Of course, it's not like if you start reading stuff for the first time, then obviously you're going to struggle with the exam. But if you can sort of keep reasonable pace, I think you should be able to do almost all of it, right? So how do you prepare? Well, of course, you need to know the concepts very well. You don't need to remember all the finer details. You need to know enough to go and look up things that you need to look up, right, quickly. So of course, if you're reading something for the first time during the exam, then you probably are better off moving on to the next question, right? You don't want to spend half an hour reading something in the first instance there. So of course, understanding all concepts is good, but you must practice. I think that's where I find some of the students who have had issues with the midterm, they haven't really put in the effort to practice. If you just read the solutions that we give you, I don't think that's a good preparation. You need to actually work through those questions yourself and then use the solutions as a reference to check what you've done, right? So I would strongly encourage that you actually practice and work through some questions yourself, because without that, it's not preparing you for the exams just by reading existing solutions. So we have given you enough content. There's lots of questions on the web page. There's the sample exam, of course. In fact, it's already visible through Inspera. I'll just make that link visible for you. Yeah, I guess that's what it all comes down to, just practicing, right? Practicing some of these questions. Do familiarize yourself with the exam environment. I mean, you did do that anyway for the midterm, but if you had any issues, might as well do the final exam in Inspera. Now, mind you, you can only do it once. So only start the final exam in Inspera when you are sure that you want to actually sit the exam. And I would actually encourage you to do that, right? Block of 2 hours and then just do the final exam as if this was indeed the final exam, right? So you kind of are in that same environment, same pressure, if you may, and that will give you some good practice. Now, one thing I may also just suggest is, in the past, we've had these issues where if 500 of you start accessing the course web page at the same time, then WebCMS does not like it. Now, mind you, WebCMS is completely out of my control. I do not control it. So since the content now is frozen, I will update this last slide sets from today and put it up there. But after that, we are not expecting to make any changes to the content, right? So might as well just download all the slides and you can sort of view them there so that you're avoiding overloading the server. On the day of the exam, obviously, some of this is quite obvious, but we often forget. So just make sure you're getting a good night's sleep, make sure you've eaten something, make sure you have water handy, make sure you're in a comfortable environment that's not too hot, too cold. Make sure your internet connection is working correctly in the room that you would sit the exam. If you're sitting far away from your access point, and then you're going to have trouble, you don't want that, right? So just make sure you're in a comfortable space. And most important thing, if a question does perplex you, if you're left scratching your head, just move on. I mean, one question is not going to be the end of it, right? There'll be several questions on the exam, so just keep moving on, and you can always come back and try working through that problem question later. So make sure you don't panic. It's not like the exam is structured in the order of increasing complexity or anything like that. In fact, it's mostly it's organized. I forget how it's organized actually, but in any case, it's definitely not in the order of increasing complexity. So it's not like the first question is easier than the last, right? So just keep that in mind. There's some questions here. Would textbook questions be a good point of reference for practicing? Certainly, yeah, the more questions you can get access to, the better. So certainly, why not? Can we send you email for consults if we have some relevant questions? So I would suggest not sending emails. I would suggest posting questions on the forum. If you've seen or if you've ever been on the forum, you'll know that I respond fairly quickly. Either me or one of the tutors will respond. And by having things on the forum, it helps other students as well, right? My email is overrun anyway, so it's better you post questions on the forum, and I will certainly send out announcements for some virtual consult times next week. So be on the lookout for those announcements. If you need to come and speak to me, you can certainly do that during the consults. Will we get the opportunity for a revision lecture? I don't plan any revision lecture. I'll set up consults. So if you have specific questions, you can ask me there, because I wouldn't even know what to cover in a revision lecture, right? There's a fair bit of content. So it's better if you have questions, you can ask me pointed questions on the forum or in the consults. So yeah, that's all really I have to say. It's been a pleasure teaching this course, albeit in a virtual environment. If at all you're on campus next year, do come and say hi. I sit in the CSE building on level 6, so it would be wonderful to actually put some of your names to a face, and you can actually see more of me than what you just see here in this webcam capture. So good luck with your exams, good luck with everything, and good luck with life in general, right? And hope you all do well. So I'll stick around if there are questions for now. If not, I'll see you online, and hopefully at some point next year when you're on campus. Bye-bye.